So let's take the occasion, and thanks to Gediminas and his team for organization of the workshop. That's actually perfect time for us. I want to contribute with the concept of spin squeezing, which can be generated with a multi-component ultracold atoms. And in our work, multi-component means also always more than two. So at least spin 1. How can I change the... Okay. But before, let me introduce the concept of spin squeezing, the typical one which was mostly studied up to now. So let's start with the grants. Actually to 1927 and the observation of Heisenberg, who said that in quantum mechanics, observables are subject to interesting fluctuations, quantum fluctuations. And he proposed some kind of inequality which estimates a product of such a limits products of such a fluctuations. Now this inequality we know as a Heisenberg uncertainty principle, which says that the product of fluctuations of two observables cannot be smaller than the commutator between them divided by 2. It means that in quantum mechanics, these fluctuations introduce quantum noise, which limits sensitivity of measurements. So if it is not related to experimental imperfection itself, if we reduce the experimental imperfections to ideal situations to 0, always there would be some quantum noise which limits sensitivity of measurement. This inequality is minimalized for coherent-like states when both fluctuations are equal each other. That's why in time people start to think how to omit these fundamental limitations, and the concept of squeezed light was proposed in 17th. Later it was observed in experiments with light. In the meantime, also people start to think maybe also in massive particles like atoms that would be possible to generate such a squeezed state. And that's 1993 when Kitagawa and Ueda proposed the concept of spin squeezing, the one which I will discuss later more, which was observed with bimodal Bose-Einstein condensates in 2010. So today, actually squeezed lights are used not only in laboratory to demonstrate squeezing, but also they are used to enhance precision of measurements. For example, when the signal is very weak, like gravitational waves in experiment in LIGO. Also, spin squeezing with ultracold atoms is not only produced in laboratory, but it starts to be taken in the proof of principle experiment to enhance precision of sensitivity in magnetic field measurement, or also now there are recent work to use them in optical clock. So what is spin squeezing about? So now let's focus on spin squeezing. We understand spin squeezing as a resource that use quantum correlations to reduce quantum noise in collective spin observable below the standard quantum limit. This standard quantum limit is like for the coherent states, which minimize Heisenberg inequality. So now we have, so how to back, I don't know. With this one, okay. So now we are dealing with the spin observable, which are here, and this spin is a collective spin in the sense that we sum up elementary spins of elementary atoms. So when we use uncorrelated atoms, then fluctuations are equally distributed, like for the coherent state, and they equal to n/4 for spin half particles. However, we can use also correlated atoms. Then we can reduce fluctuations of spin component below standard quantum limit at the expense of the enlarging fluctuations in the orthogonal direction. And in the phase measurement, when we measure angular uncertainty of the collective spin direction, coherent-like states gives the sensitivity which is proportional to the inverse of square of number of atoms, while for the spin squeeze states, we have additional factor which is spin squeezing parameter. And that's a very important parameter, very useful to calculate. It is defined here. It means it is a minimal variance in the direction in the plane orthogonal to the collective spin. So we have collective spin, we have plane which is orthogonal to the collective spin, and we search for the minimalized fluctuations divided by the value for the coherent state. It is whenever spin squeezing parameter is smaller than 1, it is a witness of spin squeezing, possibility for quantum enhanced sensitivity. Also, it is a witness of entanglement, two-body correlations. It has many interpretations that is this very useful quantity also in theory as well as in experiments. So usually there are many ways to generate spin squeezing. We'll use dynamical generation. We start with the coherent state. Today I will use unitary evolution with some Hamiltonian, which leads to the squeeze states. And actually in the literature there are very well known two families of Hamiltonians. The one is one-axis twisting, which the form is written like SZ to 2. SZ here is a collective spin once more. And the scaling of the best squeezing. So here's evolution of the squeezing parameter in time. Best squeezing is the first minima of spin squeezing parameter. So the scaling for one-axis twisting is like n to minus 2/3, while there is also a better, let's say, a family of Hamiltonians, which is called two-axis counter twisting, when the scaling is 1/n. So much better. So just characteristic features of such spin squeeze states. It is a scalability with the number of particles. So whenever when I'm saying about spin squeezing, I always have in mind scalable spin squeezing. Usually it is a power law with some alpha, which is, for example, 2/3 for OAT or 1 for TACT. So the more particle, the better the resolution, the sensitivity. With ultracold atom, it is already very well established resource. Around 2010, first experiments with bimodal BC were performed, and the level of squeezing, which they demonstrated, it was from -3 to -8 decibels. Much better, it turns out that they are atoms in a cavity, when the level of squeezing can be even -20 decibels. While also recently, Rydberg arrays were used to generate spin squeezing as well as trapped ions. These squeeze states are relatively robust to decoherence and particle losses as compared to much more entangled states like GHZ states. Also, we say that they are quite compatible with realistic experimental imperfections, because actually these effects are quite well understood with the ultracold atoms, like phase noise, the effect of phase noise or particle losses. Also, it remains useful for metrological tasks at moderate level of squeezing. So up to now, the majority of work, actually almost all work, apart spin-nematic squeezing, was done for spin-half particles, so two-level atoms, two-level systems. However, the physics and also dynamics of spin squeezing is weakly understood in the high-dimensional spin systems. So today I want to show you some results of our results where we study spin squeezing generation in two platforms which can be realized with ultracold atoms. One platform, there are spin or Bose-Einstein condensate, when pseudo-spin of particles can be 1, 2, 3, or even 8. The second platform is there are alkaline earth atoms in optical lattices, and I will focus on fermionic atoms, like strontium, ytterbium, when the spin of particles, they are 9/2 or 5/2. And here there is a beautiful picture from the recent experiments from the Letizia group, where they show that they can detect the populations or each magnetic level using quantum Gauss microscope. So it seems that high-dimensional system, high-spin ultracold atoms provide very good laboratory to understand the dynamics of spin squeezing beyond the conventional spin-half paradigm. So I want to show you now, start with spin 1 Bose-Einstein condensates. Actually our study started with the visit of Tommaso 1 year ago when he was on his way to Vilnius for the workshop. And then he just shared his observation that it is possible to generate spin squeezing with spin 1 BC. So here's a picture of Tommaso. He collaborates with Fabio and with his PhD student from the Warsaw site. It is mainly Navid, who is a PhD student in our institute, and also Jakub Krabarczyk, who is a master student. In general, spin S is related with the elementary spin of particle, of atom, contain electron spin, orbital angular momentum, also nuclear spin. There are many species in within ultra-cold atoms experiments. With rubidium you can have spin 1, 2, but also higher spin like experiment of Sylvian today. He discusses the spin can be 8. I will focus on spin 1 with 3 internal Zeeman components. The theory of spin or BC is well understood and can be found in the review paper of Ueda. So we work in the oversimplified scenario in the single mode approximation with spin 1 particles. The relevant spin-dependent interactions are written here. So it is a collective spin model, isotropic. So the coefficients in all 3 components are the same. And here S is a collective spin, sum up over individual atoms. There is an energy scale which is set by C in our case. It is related with a particle number. C1 contains scattering length, and also we have dependence on the wave function because we are working in the single mode approximation, which says that the external spatial wave function of all atoms is the same. So we can just integrate it and include in the energy scale. So if we choose our initial state as a spin coherent state, then there is no spin dynamics with such a Hamiltonian, with the unitary evolution. That's why something needs to be added. And careful analysis shows that when one adds quadratic Zeeman energy, sorry for that, it breaks the isotropy of spin interactions and could introduce some non-trivial spin dynamics. So here is the form of quadratic Zeeman energy. So there is a Q. Q is proportional to magnetic field strength squared, but also can be tuned by coupling with light. We have summation over magnetic number, m squared, and there is a operator which describes number of particles at the given magnetization level. So in general, unitary dynamics with initial spin coherent state with this Hamiltonian cannot be solved analytically. Usually, in theory, we want to have some analytical results. However, we can consider 2 limit cases when some approximated solution can be done. So let's go to the small q. So these 2 limited cases, it's a small q and a large q. So let's go to the 2 small q regime. So when this quadratic Zeeman term is treated as a perturbation. So one can try to find a model which describes which somehow approximates the evolution in the energy manifold where the initial state is. Yes, and this Hamiltonian, it is written here. When one performs perturbative analysis using Schiffer-Wolff transformation. So what we see, it is a one-axis twisting Hamiltonian, very well-known model. It is valid, it approximates well the dynamics when Q is smaller than 1, and it is valid for any spin. Psi Q set the time scale and also energy scale. It is proportional to Q, and also it is related to the total spin of atom. What is very important here, that total spin is conserved, and also there is an analytical solution which was given in 1993 by Kitagawa and Ueda. So here is an example of results for spin 1 when using truncated-Wigner approximation, because we wanted to simulate large number of atoms, 30,000 of atoms, for 2 different values of Q, deeply in the perturbative regime when Q is 0.01, and a little bit relaxed when Q is 0.1. What is plotted, it is spin squeezing parameter versus time. Blue line is exact model. Orange line weakly visible because they overlap. So here's maybe better visible, is our effective model. So what we could see, it is indeed that squeezing is generated as for one-axis twisting, and also we can notice that the time scale depends on Q when number of particles is fixed. So we could do scaling analysis to check if it works over many orders of magnitudes. So what we plot here is the minimum of the spin squeezing parameter, so it is at the bottom, versus the number of atoms. Different points corresponds to different values of Q, from blue and red and green up to green, which are deeply in the perturbative regime, up to half or even 0.75, which are a little bit relaxed. But we could see that one-axis twisting like scaling works for many values of n, over many orders of magnitudes. The same is also with the scaling of the best squeezing time. So that demonstrates indeed that this model works. Yes, yes. So usually when we define spin squeezing parameter, it is the minimal variance over the standard quantum unit, yes. So whenever it is smaller than 1, it means that we are better than standard quantum. Okay, so also here just to show that not only spin 1, but also in the case of spin 2, 3, 8, with our simplified form of the contact interactions, it is possible also to generate spin squeezing. And what is maybe worth to notice, that the larger the spin, it accelerates the time scale. Not only the level of squeezing, but also the time scale. So now the second limit, when Q is large, so still we are working with the full Hamiltonian, but now quadratic Zeeman energy cannot be treated as a perturbation, so we need to work a little bit in different way. That's why we use so-called rotated wave approximation. We go to the interaction picture, we just remove fast oscillating terms, and we back to the laboratory frame, and that's the Hamiltonian. So this is not one-axis twisting model. We have some nematic non-linearity, and 0 is the operator which describes particles in the 0, m equal to 0 Zeeman level. Also, we have some detuning. This is valid for Q larger than 1 when spin is 1. But with this Hamiltonian, total spin is not conserved. It is because of the terms which are contained in 0, which do not commute with the total spin. However, the model can be solved analytically, and it was done by Navid. And here's the result. Blue line are exact results with full Hamiltonian. Red line are results for approximated model. So that's quite strange dynamics. We see a lot of minima. However, this envelope of this minima goes more over like for the one-axis twisting dynamics. So we could see that a specific moment of time, we could recover a lot of squeezing, which are followed one-axis twisting law. However, in between, the length of the spin is 0, so we could visualize this 0 on the Bloch sphere inside, and there is no squeezing actually at all. So because of these periodic repetitions of squeezing, we call it stroboscopic squeezing. However, when one catch the minima of the spin squeezing parameter when there is a spin squeezing and check scaling with the system size, one could see that actually different points are along one axis twisting results, how the same with the scaling of the best squeezing time. So now let me switch to the another platform, different system made of high spin Fermi Hubbards, like system. More details can be found in the poster of Hubert Witkowski, who is here. He can explain more. That's the system we are dealing with. And it is described by the Fermi-Hubbard model when we have a tunneling term. So in addition to level like tunneling, we can have tunneling between different magnetic levels, and also we have on-site interactions between atoms which are at the different magnetic level. It is due to the Pauli excursion principle. This Hamiltonian, this kind of the model, can be thought in the strongly interacting regime when U dominates and with one atom per lattice site. Then when performing perturbation analysis, one could find that the model reduces to the spin exchange model. This model is exactly the Heisenberg XXX model, only for spin half. So it is not the Heisenberg model when the spin is larger than half, one or more. Operators, spin arrow operators, which are here, means that we annihilate particle in the M prime magnetic level and create a particle in the M level at the same lattice site. So this term describes the situation that there is exchange of particles between different magnetic levels, while the another term is just the exchange without change of the magnetization of atoms. Spin dynamics is not present with this Hamiltonian because initial spin coherent is eigenstate of the Hamiltonian. So once more, we need to add something. That's very characteristic that we need to add something to induce spin squeezing. So we add spin orbit coupling, the term which is written here. So we have summation of the relative side. We promote the atom spin of the atom, or the spin of the atom is lowered with some phase factor which is position dependent. In general, it is not solvable. We want to have some, at least simplified form of the Hamiltonian that we can analyze. That's why we once more, to estimate a little bit, understand dynamics, we made the perturbative analysis, treating coupling to light as a small parameter. This leads to us to the following Hamiltonian. Here, J is a collective spin. Once more, it is a Hamiltonian which describes collective spin. It is not the one-axis twisting Hamiltonian, as long as spin is larger than half. There is additional term which do not conserve total spin. So once more, the characteristic feature is non-conservation of spin. Also, it is not solvable analytically. However, we can perform exact numerical simulations. So please look at the top panel when the spin squeezing parameter is plotted versus time, and concentrate on this line, which is blue line only. That's exact solution. So what we could see, it is that at some, in below, you could, it is plotted also by this blue line, the length of the spin, total spin, squared. So what we could see that at some moment of time, the total spin is smaller, is shorter. So the dynamics is not now on the Bloch sphere, but these fluctuations somehow go inside the Bloch sphere. And the squeezing which is observed, it is not the spin squeezing which takes place in the plane orthogonal to the direction of the spin. But it is like 3D-like situation when the squeezing, the fluctuations in two components of spins are smaller than the standard quantum limits. It has a shape of, it has a cigar shape at some moments of time. So it is more like planar like squeezing than ordinarily well-known spin squeezing, although spin squeezing also can be generated at the specific moment of time. So that's everything what I wanted to show you. To summarize, spin squeezing in high spin systems can be generated. However, typically we need to add something, some coupling to external fields. In the case of spin-Auroch Bose-Einstein condensate, we observe universal one-axis twisting scaling for various small and large numbers, values of the quadratic Zeeman energy. In the case of Fermi-Hubbard system, spin squeezing is reshaped. It has different form. It is more in the direction of planar squeezing than the ordinarily typical spin squeezing. And it is mostly due to the breaking of total spin conservation, which leads to this not typical stroboscopic or planar squeezing at some moment of times. So thank you very much.
Thank you. It seems you are generating families of non-OAT Hamiltonians. Is it possible to classify them somehow and give them names if they deserve them, or non-OAT?
Actually, we are starting to work in this direction. Perhaps at some point, maybe if we found they share some common features that would be worth to have some name. But actually what we learn, what is very characteristic, it is non-conservation of spin. And that's why indeed it goes to the different behavior. Actually planar squeezing is a little bit known, not so famous as spin squeezing. So there is some characteristic of planar squeezing. However, stroboscopic squeezing I could see for the first time.
Thank you.
Yeah, very nice talk, thank you. If I assume correctly, you assume isotropic scattering, which means that the scattering lengths, let's say, between the different spins are the same, is that right?
Yes.
So did you ever look at the real atom, which is often different than the scattering lengths? Would it survive or help or hurt?
That's very interesting. I think that also should be taken into account, but not up to now. Okay. We just started with the simplest possible situation to understand the basic stuff, yes.
Yeah. A somehow related question, but in a different context. I mean, there's a lot of interest in squeezing on the clock transition, for instance, bosonic strontium. Is there also a scheme where something like going onto the lattice can help with this?
So if the spin is half, I guess it is, then for the half system, there is no possibility to break the conservation of spin. So it is, if spin squeezing dynamics is a little bit different than the typical which we observe, perhaps it is a different effect, like phase noise or another effect, yes.
Okay, thank you. But so going to 3 states, so the story there is if I go to 3 states instead of 2 states, I can win.
Yes. That's very characteristic, yes.
Thank you. Maybe one more quick question. Yeah, yes, please.
If I'm allowed, so a very general question. You mentioned that squeezing can be a entanglement witness. So for computation, it's often very difficult to pin down, like the role of entanglement, how you need it. But is it simpler that you can say that the more squeezed states are always the more entangled ones? These kind of.
So then we need to have this additional witness of entanglement. Sometimes it is related, sometimes no.
Okay.
I have no experience actually with the higher spin system.
Okay.
Yeah, thank you.
And let's applause.